Phase diagrams help us to visualize the relationships between the three different states as a function of pressure and temperature. And so the phase diagram maps the states of a substance. State and phase mean the same thing. So there are regions that represent what conditions that particular state is stable under. So you'll see a liquid as a section of the graph, and that'll tell you that under those particular combinations of pressure and temperature, the substance will be stable as a liquid. Then there are lines that divide the regions, or they're curves, more likely, and those represent sets of temperature and pressure where the substance is in equilibrium between the two states on either side. So that's where it's going to be going back and forth, like the melting point or the boiling point. And so we say there's a vaporization curve, which represents the transition between liquid and gas. There's a sublimation curve going between the solid and the gas, and there's a fusion curve that goes between solid and liquid. And these often come together in what's called the triple point, which is a unique unique set of conditions where all three states are stable and in equilibrium together. So here's the phase diagram for water. We see on the y-axis that we're graphing pressure, and it says note not to scale. They're identifying one point here, but this is not a scale drawing. And over here, they're indicating two different temperatures. Again, this is not to scale, but they're telling us here's 0 degrees and 100 degrees. Those are important points for water. Here we have the sublimation curve. Above it is the solid region. And so this tells us that at this pressure and this temperature is the point where the solid and the gas will exist together. The fusion curve shows us where the solid is going to melt to the liquid, and that temperature at which it melts changes a little bit because of the pressure. So if you increase the pressure on the ice, it will cause it to melt at a slightly higher temperature. And if you decrease the pressure, the melting point goes down. Here's the liquid to gas transition called the vaporization curve, and we see that at 760 torr, we've got a temperature of 0 degrees Celsius. That's the temperature at which the water will boil. This is the normal freezing point. As we increase temperature and pressure, at some point we get to the critical point. And above this, the vaporization curve is gone because the gas and the liquid are actually a supercritical fluid. And this is what's called the triple point. So the triple point for water is well above atmospheric pressure and just slightly above the freezing point. But you'll have gas, liquid, and solid all in equilibrium together. So we can look at this and represent changes in temperature or pressure as movement within the phase diagram. So what we can do is if we're starting here at 1 atmosphere and starting at minus 25, which is where we started with our block of ice, if we're keeping the pressure the same, we can move along the temperature axis and see what's happening. As we go to the right here and we increase the temperature, we've got solid, solid. At this point, we've got melting. It's going to melt. Now we've got a liquid. We've got liquid, 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 liquid. We get to here. It's going to boil and become a gas. You can also look at, well, what's going to happen if we change the pressure? So here at room temperature, we'll start at 1 atmosphere of pressure and increase the pressure. And we'll just increase. I'm sorry, this is decreasing. I had that other one upside down too. My apologies. we decrease the pressure, and at some point, it will form a gas at room temperature. I have witnessed it personally. It's amazing to see water boiling at room temperature. But that's so these curves can help us think about what's going on we can pick a temperature or pressure and then follow movement through this graph to describe what's actually happening to the substance. The slopes of these curves, whether they're positive or negative, is significant. For water, the fusion curve is unusual. Let's go back here a minute. Here's the fusion curve for water. It has a negative slope. As you increase the pressure, the melting point becomes lower. Most things have a fusion curve with a positive slope. Notice for carbon dioxide over here, there's the liquid and there's the solid. At, where am I? I have to locate myself. Here at 1 atmosphere, there's no stable conditions under which you would find a liquid. You go directly from the solid to the gas, and there's no liquid there anywhere. Can you have liquid carbon dioxide? Yes, you can, but you have to get above 5.1 atmospheres of pressure to do so. This is iodine. So we've got 1 atmosphere. I really don't know what else to say about that. Look, I guess we're supposed to follow the lines. I already followed line B. Follow line A. Here we have iodine at its boiling point. As we increase the pressure, it becomes a liquid, and then as we increase the pressure further, it becomes a solid. And that's not what ice does. That's not what water does.